The title of this presentation is Intertwining Vectors and Boltzmann Weight Matrices of a Solid-on-Solid 20-Vertex Model. To begin with a presentation overview, I'll be establishing some comparisons between the 7-vertex model and the 20-vertex models from the perspective of and including solid-on-solid or SOS models, Boltzmann weight matrices, R matrices, and intertwining vectors. And by and large, a lot of the perspective that I want to provide in this type of presentation from this upcoming project that I'm going to be having on the archive is that I'm pretty much talking about and discussing how one can establish some types of conclusion or observations about solid-on-solid models from vertex models. And this is really much something that's always really interesting to me and an interesting perspective in terms of what appears in mathematical physics and statistical physics, because a lot of times what happens is that individuals are maybe interested in classifying or determining whether maybe some argument or some classification about one vertex model, it could carry over or actually hold water or hold weight or remain valid for other types of models. And I'm pretty much going to be able to establish comparisons between the 7-vertex model, which is where, or the circumstance or the models from statistical physics in which an argument was first carried out, and then establishing how one can make sense of these types of notions from the solid-on-solid models for the 20-vertex model instead. And as I'm saying in the second bullet point here, with such objects and the quantum inverse scattering method, which I'm also going to try to allude to, even though there are a lot of other presentations on my channel about the quantum inverse scattering method, I'll kind of reiterate some basic objects, a few objects that one can need to understand and see the direction in which we can go for analyzing a solid-on-solid model for the 20-vertex model. We are interested in determining explicitly a set of expressions for entries of the Boltzmann weight matrix in intertwining vectors for a solid model obtained from the 20-vertex model. And like I've said in other types of presentations, like I mentioned in the channel, but I'll reiterate, what really characterizes vertex models is the fact that they have the R matrix and they satisfy the Young-Baxter relation. And basically, the intertwining vectors are going to play the role of being able to perform some type of transformation on the R matrix for a vertex model to obtain a Boltzmann weight matrix for a solid-on-solid model, and establishing the number of components on which the intertwining vectors act is really important, which I'm going to further emphasize and discuss in the adaptation of an approach from the literature that I'm going to highlight. So this is the literature in terms of the 7-vertex model that I'm going to make use of in this presentation, and it's titled Boltzmann weights and fusion procedures for the rational 7-vertex SOS model. It's from these two authors that was put on the archive a year, pretty much a little more than a year ago. And what interested me from their work is that they're really talking a lot about rational vertex models and the rational 7-vertex model, and they're making use of a fusion procedure, which is a term that's used throughout the literature to describe how one can enlarge or make bigger the solution set of the Young-Baxter equation by appending solutions to other Young-Baxter equations with the R matrix. And pretty much they demonstrate by and large from this paper that you can take a R matrix from a vertex model and be able to apply some intertwining relation, which I'll also introduce an analog of the 20-vertex model by making use of the intuition and the arguments that they give for the 7-vertex model, which can be used to obtain an SOS model, namely a solid-on-solid model. And even though the solid-on-solid model is not exactly the same as a vertex model, it shares in the commonality that there's a Boltzmann weight matrix, which can be obtained from applying some suitable transformation of the R matrix. And then by basically looking to solve a system of relations, basically turning things into a linear algebra problem, you can obtain some explicit set of expressions for the intertwining vectors by making use of a very similar strategy that these authors do, in which they pretty much set certain components of the intertwining vectors to be to 1, which without loss of generality allows them to obtain a solution set to some system of equations, which is relating to the expression of the system of expressions for the intertwining vectors in the Boltzmann weight matrix. And as another work from the literature that I found to be really interesting that I've used in some of my works, or previous works from earlier this year, is a work in the literature which discusses the universal R matrix factorization for the 20 vertex model. And it's titled Exercises with the Universal R matrix, that's provided by this large group of authors. And why I was really interested when I was reading this work and making use of this framework within the context of the quantum inverse scattering method is that these authors pretty much discuss how to construct either two-dimensional universal R matrices or three-dimensional universal R matrices. And fortunately, these universal R matrices that they provide through a construction that I'll reiterate and reproduce from their paper, it satisfies the Young-Baxter equation, which is very helpful in terms of being able to import this framework from a previous work that I did last year in which I answered an open question due to Koya Reshetikin and two of his students who were at Berkeley at the time, in which they were pretty much interested and they had suggested that an open question for establishing that integrability of a Hamiltonian flow would hold for the inhomogeneous six vertex model from basically adapting the framework from the quantum inverse scattering method. So I was really interested in thinking about how to determine or further develop an additional application of what they had originally suggested would hold for the inhomogeneous six vertex model for the 20 vertex model. And this is the work in the literature that I had described, in which some of my previous work from 2024 on the 20 vertex model earlier this year was titled Quantum Inverse Scattering for the 20 vertex model up to Dynkin automorphism. And there are several algebraic, combinatorial, and geometric characteristics that come into play when you're looking at adapting the quantum inverse scattering method from the six vertex model instead for the 20 vertex model, which is primarily relating to the fact that the previous work in the literature that I had given in the previous slide, which was titled Exercises with the Universal R Matrix, in addition to providing a factorization and a construction of the universal R matrix, also provides us with very interesting qualities and characteristics of L operators, which have several types of characteristics which actually hold up to a family of such operators up to Dynkin automorphism, which is just basically related to determining subgroups of the symmetric group. So if one even remembers from group theory or algebra, like how I took Math 4340 when I was an undergrad, it basically is looking at permutations on some fixed number of letters and determining how you can look at different subgroups within some symmetric group, which are corresponding to transpositions, which are just basically relating to either maybe performing odd interchanges of letters and odd indices or even indices and so on and so forth, and how that can actually be used to determine the action of the Dynkin automorphism group, which is determining what types of L operators can hold. And in the previous work that I had discussed with exercises of a universal R matrix, I only made use of and executed the quantum inverse scattering framework for only one of the L operators. But in fact, there's an entire family of L operators which holds up to Dynkin automorphism, which is relating to determining how some weakened notion of integrability can be determined for the quantum inverse scattering method for the 20 vertex model. And now I'm going to get more into what was the topic of discussion from the very first paper that I had given as a reference from the literature, in which those two authors from the 2023 paper from a little over a year ago, they were interested in talking about how intertwining vectors in Boltzmann weight matrices can be formulated for a rational seven vertex model, which I'm also interested in studying in the context of the 20 vertex model, namely another type of vertex model which has a higher dimensional state space, because the 20 vertex model is a three-dimensional version of the six vertex model that's defined over the triangular lattice, in addition to the fact that this vertex model has 13 additional configurations rather than its two-dimensional counterpart, one of its two-dimensional counterparts in the seven vertex model. And by and large, as I had alluded to in the previous slide, in a previous work in the literature that I had given this year, which was talking about quantum inverse scattering for the 20 vertex model up to Dynkin automorphism, a lot of those properties, when we're talking about the quantum inverse scattering framework in general, is really relating to the transfer matrix and the quantum monodomain matrices, which are used to really, which are really central objects of intense study that we look at in this field, that we try to approximate in asymptotically near infinity when the finite volume of some region gets to be very large. And I mean, that's a very common thread and a common theme in statistical physics because you pretty much want to start from a very small finite volume and take some weak infinite volume limit from which you would then like to study whether maybe correlations or whether long range order or long range interactions would emerge from the model that you're interested in studying and classifying further, as well as maybe if you vary some order parameter, whether there would be any different types of or very salient or significant differences in the behavior of your model. Whether, like for instance, from work in the literature, which has determined whether, say, correlations decay exponentially fast in or versus polynomially fast. And for the 20 vertex model, which we're going to make use of and study further in this presentation, I made use of a transfer matrix, which is given by the fact that it's dependent upon three spectral parameters, U, V prime, and W prime prime, which are depending upon each one of the degrees of freedom over the triangular lattice for which the 20 vertex model is defined. And it's given by a mapping which has the same codomain and target space, namely the tensor product of C3, namely the three-dimensional complexified space, which is a tensor product of C3 raised to the tensor of the absolute value of n plus the L1 norm of n, where n and m are positive integers which are appearing in the two upper indices of these products, which is given by the fact that one expression for the transfer matrix for a three-dimensional representation of the transfer matrix for the 20 vertex model can be given by a product of a diagonal matrix for some suitably defined function alpha, which we exponentiate of along each one of the three entries of the diagonal, as well as multiplied by this R term, which is the universal R matrix factorization, which appears in the second work from the literature that I had given from Booz and colleagues from their exercises with the universal R matrix paper. So I'm just reproducing this type of object because it's something that I had used within the quantum inverse scattering framework for a work that I had done, I think in July earlier of this year for the 20 vertex model, which is very much important because it's relating overall to the quantum inverse scattering method, as well as our ability to perform a transformation from the universal R matrix to obtain a Boltzmann weight matrix from the intertwining relation in the intertwining vectors for a solid on solid 20 vertex model. And quite simply, the factorization from the universal R matrix that was given in the previous paper, the literature is given by the product of three R terms as well as a K matrix term. And a K matrix term is often used to resemble, used to resemble boundary contributions or boundary conditions, which is even appearing in a lot of formalisms for transfer matrices and quantum monodromy matrices for spin chains. And this delta parameter is given by some strictly positive parameter, if I remember correctly, which is just given by the fact that you can segment or you can you can separate the factorization of the universal R matrix either into contributions that are less than or equal to this parameter, around the same scale of this parameter, or even greater than or equal to this parameter. And in this way, we can make use of the universal R matrix factorization that's provided by Booz and colleagues from the second literature reference I had given, which is allowing us to determine how we can make sense of the transfer matrix as well as asymptotic properties of the transfer matrices and the quantum monodromy matrices, as well as even looking at their spectrum or the spectral gap, namely the distance between the top two largest eigenvalues of the transfer and quantum monodromy matrices. And again, this is just reproducing the factors just to give the viewer an idea of the complexity and how non-trivial a lot of the factorization for each one of the components of the universal R matrix that's given in this reference that I made use of for the 2020 or for the 20 vertex model, within the quantum inverse scattering framework. For one, the first factor has some parameters that are dependent upon a Q exponential term, which is a combinatorial object that I'm not going to exactly define, but it's given by a tensor product of two elements together multiplied by some Q minus the reciprocal of Q term, in addition to the fact that other terms, the other two intermediate terms before we reach the boundary contributions from the K matrix of the universal R matrix factorization are given by the fact that it's either an exponential and a Q exponential term, as well as the fact that in this third contribution or this third term from the factorization of the universal R matrix that's given in this 2010 reference, we're taking a product over gamma over some root system. And I'm not going to exactly define in this presentation what is given by the root system, but I talked about it in other presentations on my channel from a play that's given on triangular ice for the 20 vertex model, in which I just basically further broke down what is the difference in the two-dimensional and the three-dimensional universal R matrices that are constructed by the authors in this work, and how this actually fits in within the quantum inverse scattering method, like I had mentioned, namely from the perspective that we're looking to have some type of R matrix or universal R matrix that satisfies the Young-Baxter equation, from which we can determine whether more desirable properties of integrability can hold for vertex models. And finally, the K matrix, which is the last term which appears in the universal factorization of the R matrix, is scaled in an H bar term. And this H bar term is very significant because it's really representing how the summation that we're taking in this final exponential over spectral parameters ij leading up to some spectral parameter r is also given by another tensor product, and is very much reflecting a lot of the physical realities that we have when we're doing or when we're looking on quantum mechanics, and not being able to gather infinite precision of the momentum and position of a system of particles simultaneously, which is really fitting into an original formulation of the quantum inverse scattering method due to Vadiv and Takhatan, in which they were looking at solutions to the nonlinear Schrodinger's equation and looking at ways to study transfer matrices and quantum monodromy matrices, and ultimately phrasing these types of characterizations of integrability with the Poisson bracket, which is taken with respect to a solution to the nonlinear Schrodinger's equation. And in my paper, I made use of the universal R matrix factorization, as well as the L operator, which is given here for the 20 vertex model in two, or L operators in two or in three dimensions, because you're looking at taking some asymptotic limit of the transfer matrix and being able to approximate this from products of L operators. And also, again, like I had alluded to in a playlist that I have on my channel for triangular ice and the 20 vertex model, I really discussed a lot of components of what's happening in this L operator, namely the fact that we have differential operators, which are represented by this Q raised to some D parameter, as well as other types of algebraic objects, namely the C parameter, which is a mapping into unital associative algebra, as well as AJ terms or other types of coefficients that we take the complex conjugate of, which we can use together to reduce the complexity of taking the asymptotic limit as n goes to positive infinity, as n goes to minus infinity of the three-dimensional transfer matrix, which we're using to represent and study some properties of with the 20 vertex model. And now I wanted to get more into the solid-on-solid models, because now I pretty much provided for the viewer an overview of the quantum inverse scattering method and how that relates to the 20 vertex model, and ultimately how the insights that I was hoping to gather from the quantum inverse scattering method of the 20 vertex model were relating to an open question raised by Koya Reshatikin and two of his students for the inhomogeneous 6 vertex model. And for the 7 vertex model, for the rational 7 vertex model, the authors of the first literature reference that I gave define the intertwining relation as the following: namely, you're taking the R matrix of the rational 7 vertex model, and you're acting upon it by a tensor product of two intertwining vector psi, and these two psi of u and psi of v represent the two intertwining vectors, which are just vectors with two entries. And they actually take a pretty convenient form in the literature reference I had provided earlier for the rational 7 vertex model, because it's either the first component being 1, because 1 in the first component of each one of the intertwining vectors represents that when the authors were solving a system of relations for obtaining the intertwining vector in the Boltzmann weight matrix that I had alluded to previously, without loss of generality, they set these components of the intertwining vectors to be 1, from which they can then determine the remaining non-zero or non-constant component of the other intertwining vector, which is very close. It's pretty much a magnification of the spectral parameter u. But what happens is that the left-hand side of the relation can be used to obtain the right-hand side of the relation, which is given by a summation over b prime, where b prime is just some point between a and c over the square lattice. And what we're doing is that we're intertwining or reversing the set of the order in which the spectral parameters are applied, in the sense that on the left-hand side, we have psi of u and psi of v. On the right-hand side, corresponding to the action of the intertwining vectors on the Boltzmann weight matrix W of the solid on solid seven vertex model, we're looking instead at psi v and psi v. But what we also change is that rather than having A and B and C on the left-hand side corresponding to the action of the R matrix for the rational seven vertex model on the intertwining vectors, instead we're having A and B prime and B prime and C, and we're taking a summation over all possible values of B prime. So we can pretty much imagine that when we're looking at the solid on solid model for the rational seven vertex model, when we're looking at also reversing the order of the spectral parameters, we're summing over all possible intermediate points B prime over the score lattice, and we're also reversing the order in which the Boltzmann weight matrix W for the rational seven vertex model is applied. Because for the R matrix of the seven vertex model, it's applied to the left, whereas for the other term, it's applied to the right. And pretty much we can make use of a very similar type of relation for the 20 vertex model just by one, increasing the dimensionality of the two intertwining vectors by one component, because we're defining something as a three-dimensional vertex model over the triangular lattice, in addition to the fact that when we're looking to solve the system of relations that I had alluded to that the authors were looking at for the seven vertex model, for the 20 vertex model, instead, we're going to make use of the universal R matrix factorization from the literature, or from the second literature reference I had given, which is allowing us to just basically solve a system of equation that has countably, a finite number of more relations, which can just be obtained from reading off the additional entries from the factorization of the universal R matrix that I had given and reproduced from the 2010 reference on exercises with the universal R matrix. So in this way, we can really be able to establish pretty simple comparisons between the seven vertex model and the 20 vertex model, and just being able to turn things into a solution set for a system of linear equations that can be read off from the R matrix and the Boltzmann weight matrices, from which we would like to obtain the intertwining vectors in the action of the Boltzmann weight matrix. And as we have been alluding to, for the solid on solid 20 vertex model, one can begin to write the system of equations from which the intertwining vector and Boltzmann weight matrix are obtained. And for the first entry of the universal R matrix, the equations take the form of this form. What I pretty much did was that, just to simplify notation a little bit, I'm just going to denote the first entry of the universal R matrix from the factorization that's given by R with just script R sub 1, which is then also going to have, oh, sorry guys, that's a typo. The W term should be on the other side, but basically it like just goes to show how one can make use of the intertwining vectors that are given for the 20 vertex model, and how that relates to the Boltzmann weight matrix for the solid on solid model. And again, like we can see, as I alluded to previously, is that in the left-hand side of all the equations for the system, we have U and V, but on the right-hand side of all the systems of the equations, we have V and U. So we're applying the intertwining relation, which is reversing the order in which the spectral parameters U and V for the 20 vertex model over the triangular lattice are applied. And yeah, apologies again, it's a typo. It should be W sub 1 is given in terms of the right-hand side of all these equations that are given in this system of relations. And the intertwining vectors for the solid on solid 20 vertex model are dependent upon three components. And this is just really formalizing and establishing more context to what I had alluded to earlier, in which to be able to apply a similar type of formalism as what was provided from the authors in the first literature reference for the seven vertex model. For the 20 vertex model, the fact that each one of the intertwining vectors is dependent upon three components instead of two components is going to just result in a system of equation that has a little bit more of relations, but that we can still solve for explicitly by making use of a similar approach to their strategy, namely without loss of generality, setting some of the components of the intertwining vectors to be one, so that from the system of relations, we can obtain the remaining desired components of the intertwining vectors. And one can form the remaining equations for the system given previously for the first entry of the universal R matrix with some of these relations, in which pretty much what we want to think of is that we're taking some product of components of the intertwining vectors beta sub L and beta sub L plus 1, and we have V and U. And as one aspect of the intertwining relation, we can either switch, as I had alluded to, the order in which the spectral parameters for the vertex model are applied, or even we can look to be able to reverse even the beta sub L plus 1 and the beta sub L, which is pretty much almost having the same type of effect. So this is really a way in which, as I had mentioned, the intertwining relations for the 7 vertex model over the square lattice, they can be established also over the triangular lattice for the 20 vertex model, and that really allows us to make use of properties of the R matrix to deduce some favorable properties and qualities, namely explicit expressions for the SOS Boltzmann weight matrix for the 20 vertex model. And in general, the remaining equations of the system for obtaining the intertwining vector, the Boltzmann weight matrix of the solid on solid 20 vertex model, take the form. They just take this form, which is just given by the fact that we're applying the universal R matrix script R independent of the first entry to each one of the products of the intertwining vectors. And again, sorry, this is just a typo. The Boltzmann weight factors W should be given on the opposite side, because we're just reversing the order of the order in which the spectral parameters are applied. Namely, on the left-hand side of the relations, we're having U and V, and then whereas on the right-hand side of the relations, we're having V and U, as well as an application of the Boltzmann weight matrix W. And hence, the desired solution set decomposes into the set of 16 relations, which is just given by this form, in which we can decompose each one of the first contributions from the universal R matrix from each one of these 16 relations, which is then allowing us to deduce some type of relation in terms of interchanging the order in which the intertwining vectors are applied, as well as the Boltzmann weight matrix. And component-wise, we can express the system of relations from the previous slide with the following, namely that the R sub 1, term, namely the first term of the universal R matrix, which is appearing in the first relation, is given by a difference of two spectral parameters U and V over the triangular lattice, which is used to relate to the difference of these same two spectral parameters from the 1, the first entry of the Boltzmann weight matrix. So the Boltzmann weight matrix and the universal R matrix, they very much have many similar characteristics, namely from the perspective that both of these matrices, they have the same types of dimensions, and you're just applying an intertwining relation from all the entries that are obtained from the universal R matrix construction from the second reference in the literature that I provide, which can then be used to transform this to some type of Boltzmann weight matrix for the solid on solid model for the 20 vertex model. And furthermore, the solution set from the relations that we expressed in the previous slide can be expressed in terms of the following union of relations over I, where I ranges between 1 and 16. So just basically because we had expressed star of 1 as this set of relations, we can obtain the entire solution set, which is going to provide for us the explicit expression of the intertwining vectors as well as the Boltzmann weight matrix from the solution set of the system of relations from applying the R matrix to the universal or to the tensor product of the intertwining vectors, which is decomposing into just the products of each one of the individual 3 components of the intertwining vectors, which can then be used to relate to on the right hand side of all the equations, interchanging the order of the spectral parameters of the 2 intertwining vectors, and then applying the Boltzmann weight matrix W of the solid on solid model. And as we had alluded to, just to conclude, the main result is that the intertwining vectors in the Boltzmann weight matrix for that solid on solid 20 vertex model, which is just basically given by a little theorem that I have in the upcoming project, which is given by the solution sets to the system of equations for the Boltzmann weight matrix of the SOS 20 vertex model, which is exerting the existence of 3 constants, script or math cal C sub 1, C sub 2, C sub 3, and script C sub 1, for which the Boltzmann weight matrix W obtained from the intertwining relation equals these 3 constants. So these are just constants that are dependent upon L, some strictly positive parameter, as well as the spectral parameter underline U, which is given by the spectral parameter that I just denoted as U over the triangular lattice. And it's just basically given by the fact that adopting the notation from the literature reference I'd given for the solid on solid model from the seven vertex model is given by the fact that we can look to apply some type of intertwining relation, which is dependent upon the spectral parameter U of the triangular lattice, which can be expressed in terms of some constant which is dependent upon the length, or the L, which is some strictly positive parameter, and the spectral parameter itself. And in the paper itself that was given originally for the rational seven vertex model, the authors pretty much express the action of each one of these Boltzmann wave matrices for the rational seven vertex model for the corresponding solid on solid model from the that's obtained from the R matrix of the rational seven vertex model, which satisfies the Young-Baxter equation in terms of just basically being dependent upon something that's very close to some summation of spectral parameters or some quotient of spectral parameters over the square lattice. So we're really able to reflect similar types of characteristics, namely the dependency upon the Boltzmann weight matrix of the spectral parameters also for the solid on solid 20 vertex model. And what we also have in terms of this main result is that the intertwining vectors take the form, namely that we fix some parameters a less than or equal to b prime less than or equal to c, which are vertices of the triangular lattice, which is given by a similar type of form of the intertwining vectors that are given for the rational seven vertex model that I had drawn the attention of the viewer to, namely that we can set the first two components to be one without loss of generality, from which we can isolate from the system of equations from the system of relation that I had given in the previous slide, which are expressed in terms of the R matrix and the Boltzmann weight matrix for the solid on solid 20 vertex model, from which we can obtain the final component of the intertwining vector, namely the third component, which is dependent upon some parameter that's also dependent upon, or some constant, which is also, or some quantity, which is also dependent upon some strictly positive parameter L, as well as some other parameter U, which we just abbreviate as script C sub 1. And whereas the other type of the remaining, or the form for the remaining intertwining vector of the solid on solid 20 vertex model is just given by a very similar expression, but the reciprocal of the last component which appears. So this is again just very much relating upon the fact that it's very closely reflecting the fact that the intertwining vectors for the rational seven vertex model, as I had alluded to and pretty much provided some detail to, when the authors are solving that system of equations, they very much obtain two vectors for the intertwining vectors, which can be applied to the R matrix of the rational seven vertex model, which are very similar to each other. And in this case, for the 20 vertex model, again, we're able to recover a very similar set of expressions for these three entries of each one of the intertwining vectors for the 20 vertex model. In conclusions is that we discussed the vertex models ranging from similarities and differences between them. We introduced the 2023 work from the literature on the seven vertex model, as well as the connections that this work has with the solid on solid models, in which we're basically able to perform a transformation from the intertwining vectors of an R matrix to obtain a Boltzmann weight matrix, which can also be pretty much discussed and discussed and made sense of and analyzed also for the 20 vertex model, given a universal R matrix factorization that I introduced. And in doing so, we motivated the applications of the work from the seven vertex model within the QISM, quantum inverse scattering framework, from which we discussed the systems of relations and related structures for the solid on solid 20 vertex model. And this preprint is coming to the archive really soon. I'm really sorry again for just some minor typos that I had in the presentation that I'm going to correct in that preprint, but I still hope that it got across a lot of the main ideas. And thanks so much for watching.